Hi guys, my name is Hector and today we show you how you can start programming a autonomous routine using PID functions using Lightning. Well, the PID is a proportional integral and derivative controller. Basically, it's the most common controller you will find in the VEX because it's easy to use and it's very awesome. You can implement PD basically wherever you want, for turning, for driving short distance, and maybe in the real life you can put a PD controller for your AC. So, well, there are a lot of areas. Well, in Lightning, there are different motion functions that will use inter PD controllers to drive to certain distance you road and also make some nice turns. So let's take a look. However, the function performance, it depends about the tuning of the PD controllers, and tuning means basically to find the sweet spot and the good values for each parameters. So first of all, let me introduce you to each parameter. There are three main parameters in the PD controller. The first one will be the proportional gain. It's related with the proportion, so you have a great proportional gain, you will have a more aggressive response of your PD controller, and you have a lower proportional gain, you have a slower reaction. So it's important to find like some value that is good enough to get to a target and is not aggressive but not slower. You get me, right? Then we have the integral gain. Basically, it depends about the integral, and the integral part allows you to prevent the steady state error. Basically, if you're using PD control before, you know that when you're tuning, maybe your robot gets too closer to the target but is not on the target. So basically, integral help us to prevent that and make the robot go to a target the more closest possible. Then we have the derivative gain. Basically, it controls the derivative part and allows you to prevent oscillations and also overshoot. But be careful, because if you increase a lot the KD, basically you will have like more oscillation and more sensitive to noise. But if you have a lower derivative gain, basically you will have a lot of oscillation. So I said before, you need to find like a sweet spot to start playing. There are different methods, but maybe at the beginning it's kind of tricky to find that sweet spot about all the parameters, but you can make some research, so implement maybe a good method to tuning. There are some mathematical tuning methods, but for example, you can use the Ziegler method that basically is you can start increasing KP until you see like your robot is overpass the target, and then you can start adding the derivative part and then make the robot get closer to a target, and then you can start using integral. But obviously, just take it easy, is kind of practice and then make some research. Well, basically it's not that difficult, so you just can start testing. To use the function that I will show you in this video, basically you don't need to have a dummy tree. So it doesn't matter you having a dummy tree, or maybe you are just using your chassis, because the function uses the IMU and the integer encoder. So don't worry, you don't have dummy tree. With that established, we can just jump to the examples and start coding. In Lightning, we introduce and we use more parameters that commonly are used in the PD, but it's kind of easy, and basically the most important is the said before, the proportional, integral, and derivative gains. So let's start. First step is going to the example project and then going to the autonomous function right here. You may have like more lines here, so you can delete it or leave it, it doesn't matter. Basically, it's important to start coding here in this function, because when we're running the autonomous period, these functions that we here will run. So you will find that we have this function, this line, so don't delete it. Basically, it's a function that I put for you. It's a multitask, and basically the things that do is that print information about your system in the brain screen. So basically, you're having a dummy tree, will print the X and Y and the heading of your robot, and also updating the position using the dummy tree. But if you don't have a dummy tree, just will display the orientation of your robot using the IMU. So don't worry, don't delete that function, and everything will be okay. Well, the first function that I will teach you is basically the turn absolute. Basically, this is to turn your robot to a certain orientation. So if we take a look, I will copy this function first, and I will copy here to the code. As you can see, basically we are tuning our tune PD controller, so we are setting the proportional and integral and derivative gains, and then we have another parameters here. Basically this max basically is the maximum PD output, so you can limit to the maximum output. Then we have a scale. Basically, the scale if we search here is the PID scale. That means that basically you have 1 is mean that you're using the full power, but you can limit the output of the PID. Basically, using a decimal, that means that in this example is like the half of the power, but we set it just to 1. And then you can set the integral, power limit, and the derivative tolerance. So basically the derivative tolerance means how much the derivative part will affect, and then you can set the maximum value for the integral. One way to calculate that integral power limit, basically you can create a variable, then you can say the amount of output, in this case will be 35 RPM for example, and then you divide it by the value of the integral gain, in this case this value. Then instead of just putting a number, you can put this variable, and basically you are setting the integral power limit. In addition, it's important to set exit condition. Basically this condition helps the robot to stop basically when one of these conditions is met. So basically we have the error tolerance that will be plus and minus 1 degree in this example because it's the PID for turning. Then we can set the jump time. Basically will be the time in milliseconds that the robot will stay in the target. And then we have the stop time. Basically if the robot doesn't get the target in 2 seconds, the robot will stop. So once you declare the turn constants at the exit condition, you can start making your robot turn to a certain orientation. To that we can use the following function that is called turn absolute. Here basically we can say that makes the robot turn to a certain absolute orientation using the turn PID, the same that we are turning right here. So you can put the amount of absolute orientation, for example 90 degrees, or you can put 180, but you can also specify directly the unit, so you can tell like this is 180 degrees, or maybe you can use radians if for some reason you want to use radians. But for me, everything that I'm use that function, I always use degrees because like it helps me to know what units I'm using. So you need to remember that this is for absolute orientation. So basically you're not telling the robot how many degrees you want to turn. Basically you're saying what orientation you want the robot reach. Then if you want to tell directly to a robot how many degrees you want to turn, you can use another function that is called turn relative, and then you can turn the robot certain number of degrees. Well, will be positive if the robot needs to turn right, or negative if the robot turn left. So basically you can here 30 degrees, and that will make the robot turn 30 degrees to the right. In this case, the absolute function, the spin direction is determined basically to the less travel. So basically it is more fast to turn right to reach certain orientation, the robot will turn right, and if it's more fast to turn to the left to reach certain orientation, will turn to the left. Honestly, I recommend you to always use the turn absolute. Can be kind of difficult to start used to using just absolute orientation, but I think that is a better and clever solution. The following function is swing turn. Basically a swing turn is to turn your robot to a certain rotation, but at the same time you will block one side of your drivetrain. So it will be very similar when you try to turn and driving a real car. So it's important and can be useful because at the same time you are changing the orientation of your robot, you can start moving your robot. So it can be useful. So let's get started. The first step to using swing turns, basically the first is to tune the swing PID. The reason why it's a different PID is because basically you are just motorizing one side. So that is the reason why. So I'll just copy these lines over here, and I will copy right then. And then I will just change, instead of turn I will put swing. And well, I can set the same parameters right here, but maybe I can be more aggressive because I will just using one side, for example. Finally, we can use the swing absolute function. So we just type the name of the chassis and then swing turn absolute. It's very similar to turn absolute, but in this function we need to set which side of the drivetrain will we block. So for example, I will type lightning, then swing direction, and here we can decide with what side of the drivetrain we will block. In this case, I will block the left side, and then I will say the orientation that I want to reach. So for example, could be 270 degrees, for example. And then you can start using more of this function. For example, on the other hand, you can block the other side. For example, right swing, that means that the right side will be blocked, and then we can just like target, the target rotation will be maybe 90 degrees, and you can use this function. On the other hand, you can use another optional parameter. Basically, the block side you can not block at all and just add like a small speed if you want. Honestly, I just use this function right here. On the other hand, there are another swing turn function that is for relative orientations. So you need to set as well the side that you want to block. For example, in this case, I will put the left swing, and then you can put the amount of degrees that you want to robot turn. So for example, 30 degrees to the right will be in this way, and you want to the left, just a minus sign. So this is everything for the swing turns. The final function is drive distance. Basically, this function is very important because you can have accuracy and precision to try to reach a certain point. So for example, you can tell to your robot, well, drive forward 24 inches, or maybe drive forward 1 foot, 3 tiles. So it's very important because you have precision. It is one of the most important functions that we will find in VEX and also in Lightning. So this function, we're using two PID controllers. One is to control the velocity of the robot to drive certain distance using the integral motor encoders, and use a turn PID, the same that we said before. So basically use the IMU to prevent like deviation in the robot. So in that way you can be very sure that your robot will drive straight forward. So your robot will be straight when you're trying to drive certain distance. So let's take a look how we can use the drive distance function and how we can tune the PIDs. As I said before, basically you need to have tuned your turn PID so you can use like the same. For that reason, I recommend you to, the first PID to tune is the turn PID and make some turns and just tune, and then you can use the drive distance function. Then we need to tune the drive distance PID. Basically you can just copy, paste, and just change this for drive. And this PID controller will be very sure that you need to change and you need to start playing with these constants. But basically once you get this PID tune, basically you can start using the other function. So you can type my chassis drive distance, and then you can put the distance. For example, the default unit is inches, so you can put like 24 inches, and then you need to select the orientation that you want to block. So in this case, for example, that your robot is moving forward in the rotation 0, so you put 0 in this way. The important of this function is that you can use a copy variable, so you can put like 0 degrees, and here you can put a unit right here, so you can specify you want inches, you want foot, you want tiles. For example, that means that the robot will run 1 tile, or maybe you want to run inches, so for example 40 inches. Maybe you want to run 1 meter, so you can just put 1 meter right here. So this is important that you can use to copy units, and it's very helpful. So for example, in this way your robot will run 24 inches by blocking the orientation, so we'll drive straight. Then for example, if you want to drive certain distance but you need to change the orientation, let's suppose that you want to drive another distance but your robot is looking to an area orientation, so you can do like 30 inches, then you can put the orientation. In this way will be 90 degrees, and that will block the orientation and make your robot just drive straight. And if you want to go in reverse, just need to put a sign in, minus sign right here, so that means the robot will run reverse. That will be everything for this video. Thank you for being here. Today we'll learn how to implement PID functions to drive our robot and turning. In the next video I will show you how you can start using a tunnels function using odometry, so that means pre-pursuit, moving to certain points, and so on. So thank you and stay tuned.